and discussion is open. Yeah, Professor Kilina, you are welcome to ask questions.
Actually, would like to have a discussion for this very last question, which Connor asked himself about the temperature for the electrons. Yeah, it is true that, of course, temperature depends on the, the velocity depends on the temperature, right, proportionally. However, what do you know about electrons? The energy is quantized, right? Which means energy just gives some amount of energy. You need to give exactly the amount of energy, which will be equal to the difference between electron in the ground state to the another next electronic state. And just think about atoms. Electrons in an atom, not in a molecule, not in a specific material, not in a dye, just in an atom. What do you think the split in atomic levels would be? What is the hydrogen atom, for example, right? So for going from the first ground state to the next excited state for the hydrogen atom, what exactly the energy would be comparing to the temperature?
I'm not sure.
Okay, then let's put it this way. Electrowave radiation. You go infrared, right?
Oh, like
call it in these terms. Do you expect it to be in a visible range, in the ultraviolet, in the infrared, in the microwave, the radio wave range, X-ray range, and so on?
The IR to UV visible, ultraviolet to visible range.
The electron from the ground state to the excited state, IR to the visible, and you think in IR, infrared, would be enough to get the excitation of electrons?
When I was doing the research, they talked about that IR and Vis were the main absorbances for the dyes.
Actually, it's really rare materials where you really have this electronic splitting being so small. It's usually much bigger than infrared energy. Visible range, ultraviolet, right? For molecules, like if you're really talking about dye molecules, then the go from the first initial state to the, first ground state to the, ground state to the initial, first excited state. This is probably UV, maybe red, maybe green, but this is UV range.
Okay.
And infrared is really, this is a range where your atoms are moving. So technically when you heat, the range of temperature to get to the same equivalent to the, let's say, the energy of the red color would be huge. More than 1,000 kelvins. So really to excite the electron from its ground state to the excited state through temperature would require huge amount of heat. You really need to get to the very high temperature to really do it through the heating. So what you really can heat, you heat the motion of nucleus, because this is where they absorb light. They absorb in the infrared and kind of start doing this vibration more actively. And then you increase, with temperature, you increase the motion of nucleus and you increase the coupling, the interaction between nucleus and your electrons. Right? So that's why formally you're right, that of course increasing temperature helps to increase the kinetic energy of electrons. But this is not really a way to really do it, because you really then have to think about huge energies. On one hand, on the other hand, you always will increase the energy of your nucleus. And it means that you, overall, if nucleus move more faster, they also probably interact with electrons in a more stronger way. So you also increase this interaction with nucleus, which not necessarily a good thing to do for, if you're really interested in the transfer of electron from the dye to somewhere, right? Maybe it helps, maybe not. It really depends on the intrinsic properties of the system. But for sure, if you excite the electron to the higher states, right? If you go from the ground state to the first, second, and so on, if you really excite your electron through the light, just absorbing the light, light in the visible range, UV range, wherever the molecule is absorbing this light. If you excite the dye, then electrons go into their more excited states, their kinetic energy increasing, their momentum increasing, right? Then, of course, this would be the best way to go with higher energy electrons. So technically, you can, of course, think that increasing kinetic energy through lighting, shining light on a molecule, would be the good way to go. rather than through the temperature, through the just heating, because this would be very, very inefficient way to do it.
Mm-hmm. Thank you.
But thank you for thinking about it. I think it was a really great presentation.
Thank you.
So, any additional specific questions to Connor? So he was considering the transfer of photo-excited dye, electron in the photo-excited dye to the semiconductor due to additional heat. If there are no more questions, let's thank Connor once again. Oh, question? Dr. Han is asking, what is the ground state energy for hydrogen?
I apologize, but I don't know that right off.
That's okay. Let's make a guess. So, in which units you were doing your calculations? And anyone from the class is welcome to give a hint.
We also give a hint. I'm not sure was it helpful or not, but have you heard about Rydberg constant?
I have not.
Really? Okay.
In which units all calculations are done? Zane, Jared?
Atomic units.
Atomic units. So yeah. Atomic units or Hartree units of energy. And these units were specifically designed for problems like what is the lowest energy of hydrogen. So the answer should be like 0 plus minus 1, something like this. So
okay.
First, since atomic hydrogen is stable, would the ground state energy will be positive or negative?
Ground state energy, shouldn't it always be positive?
No. If there are potentials that attract things together, there could be negative energy. Right?
Okay. Yes.
Will the ground state energy of hydrogen will be positive or negative?
Negative.
Good. Now, if we are doing everything in atomic units, so let's just guess and make several attempts. So it will be minus something.
Minus 1 atomic units?
Twice as less.
What was that?
Very close. Twice as less.
Sorry, I couldn't get that last
Twice
part.
smaller.
Smaller?
2 times smaller.
0.5 atomic units?
Minus 0.5, yes.
Minus 0.5 atomic units.
And it is minus 13.6 electron volts.
I'm not 100% sure, but I think the formula for the calculating the energy of the electron is just Rydberg constant divided by n square. Rydberg constant can be divided in atomic units, in electron volts, and in joules. In joules, it's something 10 to minus 19. I don't remember exactly what's the value, but in electron volts, it's minus 13.6. If you say it's 5 times atomic units is 20.
0.5, 1/2.
Okay, yeah, then it's minus 13.6 electron volts. This is a Rydberg constant for the first state of the, and the formula is R, Rydberg constant, times 1 over n square, whereas n goes with your quantized number. For the hydrogen atom, n cannot be 0 because you cannot divide by 0. You go with n equals 1, 2, 3, 4, and so on. Right? And yeah, it is negative because it is attractive potential.
And it is much easier to memorize in atomic units. Okay, any other questions? If no, let's take corner of the book. Thanks for your presentation.